Billions of dollars have been invested in a massive steel pipeline approximately 356 miles long. It runs across rocky mountains, vast open plains, and areas with almost no access roads. This is the Néstor-Kirchner gas pipeline, the largest energy infrastructure project in Argentina's history. Its mission is to create a stable flow of energy, linking gas fields isolated deep underground with the country's entire national economy. To make this possible, tens of thousands of steel pipes must be transported, welded, inspected, and buried underground with near-zero margin for error under intense schedule pressure. In this video, Mandarin Tech takes you behind the scenes of a true mission impossible, where heavy machinery operates under enormous technical pressure, and Argentina's energy future is placed on a steel artery running across the continent. On July 9, 2023, Argentine President Alberto Fernández announced the inauguration of Phase 1 of the gas pipeline project, named after former President Néstor Kirchner, with a total investment estimated at approximately $3 billion. The project was built to transport natural gas from the Vaca Muerta field in Neuquén province, one of the world's largest unconventional oil and gas reserves, to consumption centers and the national gas network in central Argentina. Without fanfare or spectacle, each completed meter of pipeline is gradually transforming resources buried deep underground into a flow of energy capable of directly serving the national economy. At a time when global energy prices are highly volatile and imported supplies are becoming increasingly expensive, this pipeline allows Argentina to operate its economy with greater autonomy, especially during peak winter demand. More than just technical infrastructure, the Néstor-Kirchner pipeline functions as an energy lifeline, helping stabilize supply, reduce import costs, and lay the foundation for long-term industrial development. For Argentina, this is not merely a construction project, but a strategic shift, where the nation's energy future, economy, and geopolitical standing are placed into a single flow, quietly operating beneath the ground. Argentina is one of the countries with the largest natural gas reserves in South America, particularly in the Vaca Muerta region, one of the world's largest shale gas fields. However, for many years, this potential was largely trapped underground due to the lack of transportation infrastructure that was both large enough and reliable enough. Existing pipelines built decades ago no longer have the capacity to carry gas from production areas to major consumption centers in central and eastern Argentina. The result has been a prolonged energy paradox. A country with abundant gas reserves still forced to import liquefied natural gas at high cost, especially during winter when heating demand rises sharply. This situation has not only placed heavy pressure on the national budget, but has also made the energy system more vulnerable to geopolitical disruptions and global market volatility. Against this backdrop, the Néstor-Kirchner pipeline emerged as a project of vital importance. It is not merely an isolated construction effort, but a strategic decision aimed at restructuring the entire national energy system. The pipeline was designed to become the main gas transport axis, directly connecting Vaca Muerta to the national gas network, opening the path toward energy self-sufficiency and reducing long-term dependence on imports. The project was implemented in phases, with the initial phase focused on building a main trunk pipeline stretching hundreds of kilometers across multiple provinces and diverse types of terrain. Instead of constructing the pipeline sequentially from the starting point to the end point, the entire route was divided into multiple segments, each assigned to a dedicated construction crew. This organizational approach allowed dozens of kilometers of pipeline to be built simultaneously, significantly shortening the overall completion time. Each construction crew operated like a mobile factory, fully equipped with trenching machinery, pipe lifting equipment, welding units, inspection systems, and backfilling tools. These crews had to coordinate closely with one another to ensure that progress remained balanced along the entire route, avoiding situations where one section was completed while others fell behind. Alongside the pipeline construction plan, supporting components such as pipe storage yards, access roads, technical stations, and quality management systems were developed in parallel. This coordinated deployment enabled continuous site operations, reduced idle time between construction stages, and minimized risks arising from interruptions in the construction process. Before the first section of pipe is laid into the ground, the entire pipeline corridor must be carefully surveyed and prepared. This step is particularly critical because the route passes through areas with very different ground conditions, ranging from agricultural plains to zones with weak soil or undulating terrain. Beyond geological factors, environmental and social considerations are also taken into account. The pipeline must avoid densely populated areas, important farmland, and ecologically sensitive zones. Any adjustment to the route results in changes to design and construction planning, making the initial survey work one of the most decisive steps for the project's success. Once the survey is completed, land clearance operations begin. The pipeline corridor is widened enough to allow heavy machinery to operate while still complying with environmental and safety requirements. When the site is fully prepared, trenches are excavated to the specified depth and elevation, laying the groundwork for the subsequent installation stages. Because it serves as the main gas transmission line, the pipes used for the Nestor-Kirchner project must meet stringent technical requirements. The pipes have large diameters, thick walls, and are manufactured from high-strength steel to ensure they can withstand continuous operating pressure for decades. The steel material must not only be strong, but also sufficiently ductile to resist cracking and accommodate minor deformations caused by ground movement over time. In addition to pressure resistance, the pipes must meet safety requirements in the event of large temperature fluctuations or mechanical stresses from the surrounding environment. A small crack or a poorly executed weld could lead to serious consequences, which is why technical standards are set at a very high level from the design stage onward. All pipes are designed to operate in a buried environment, where they are exposed to moisture, chemicals in the soil, and seasonal temperature changes. As a result, corrosion-resistant coating requirements are mandatory. This coating acts as a protective shield, extending the pipeline's service life and reducing the risk of leaks during long-term operation. Construction of the pipeline can only begin once fully compliant pipe sections have been completed at the factory. This process takes place within a closed heavy industry production line, where every stage is strictly controlled to ensure uniformity across the entire system. The process begins with high-strength hot-rolled steel plates. Before forming, each plate is carefully inspected for chemical composition, tensile strength, and ductility. Only plates that meet the required standards are allowed to proceed. From their initial flat state, the steel plates are gradually bent to form the pipe body, with the bending radius tightly controlled to prevent the introduction of residual stresses. Once the two edges of the steel come together, longitudinal welding is carried out using submerged arc welding technology. This method produces deep, uniform weld penetration and achieves mechanical strength close to that of the base material. After welding, the pipe is round-shaped and dimensionally calibrated to meet the exact design diameter, making it ready for the next inspection stages. After the steel pipes are fully formed, they must undergo a series of rigorous inspections. Only pipes that pass all of these inspection stages are allowed to proceed to surface treatment. The pipe surfaces are cleaned using steel shot blasting, then coated with specialized anti-corrosion layers. This is the final step before the pipes leave the factory, where they are marked for traceability and prepared for transport to the construction site. The finished pipe sections are transported by heavy-duty trucks to staging yards along the construction route. Transportation is carefully planned to avoid damaging the protective coating and to minimize pipe deformation. Upon arrival at the site, the pipes are unloaded and laid out along the road, parallel to the excavated trench in the correct installation sequence. This staging method allows construction crews to connect pipes continuously without repeatedly moving materials, while also reducing waiting time between work stages. In sections with complex terrain, the pipes may be slightly adjusted or field bent to match the actual route alignment. When installation begins, each pipe section is lifted off the ground by specialized lifting equipment and aligned so that the two pipe ends are straight and coaxial. Alignment is a critical step, as even a small misalignment can affect weld quality. Once aligned, the pipe sections are welded together directly on site using circumferential welding. The weld is applied in multiple layers around the entire circumference of the pipe to form a continuous pipeline. This stage determines the safety of the entire route, since any leakage or defect could lead to serious consequences once the pipeline enters operation. After welding is completed, the joint is not immediately buried. Inspection procedures are carried out to ensure the weld meets technical requirements. Only after the joint passes inspection is the welded area surface treated and recoated with anti-corrosion protection, restoring continuity of the protective layer along the entire pipeline. The assembled pipe section is lowered into the trench using synchronized lifting equipment. Lowering is performed slowly and in a controlled manner to prevent pipe bending or damage to the protective coating. Once the pipe is positioned according to design specifications, the trench is backfilled layer by layer and the ground surface is restored. After a section of the route has been fully installed and backfilled, the system undergoes full line pressure testing. This is the final verification step before the pipeline is officially put into operation. Once operational, the Nestor-Kirchner pipeline will not only significantly reduce Argentina's dependence on imported natural gas, but also lay the foundation for future expansion of energy infrastructure. It is a long-term strategic project, transforming underground gas resources into a stable flow of energy that supports economic growth and national energy security for decades to come. But before gas can flow through these massive steel arteries, its journey begins in a far harsher place: remote oil and gas rigs, where energy is first brought to life from deep beneath the rock. Long before steel fortresses stood against towering waves, long before drill towers pierced the heat of the desert, the ground itself was the first laboratory of the petroleum industry, and it was here that humanity uncovered a truth that would alter the fate of the modern world. Vast reservoirs of oil and gas had been sleeping inside ancient rock layers for millions of years. The first commercial oil well drilled in 1859 in Titusville, Pennsylvania, was only 21 meters deep, yet it opened the door to an entirely new era. From that moment on, oil and gas became the fuel that lit street lamps, powered engines, pushed the world into the industrial age, and eventually bound global civilization to an energy source more tightly than any that came before it. Even today, despite the awe-inspiring offshore platforms operating in deep water, 70 to 75% of the world's oil and gas production still comes from land. The great oil fields of Saudi Arabia, Texas, Iran, and Siberia run 24 hours a day, functioning like colossal machines that never sleep. Building an onshore drilling operation begins with seismic surveys to see beneath the surface and locate formations likely to contain hydrocarbons. Once a drilling site is chosen, an area spanning tens of hectares is cleared, leveled, compacted, and reinforced to support a 45-meter-tall drilling derrick and hundreds of tons of equipment. Drill pipes made from segments of ultra-strong alloy steel are joined together and lowered into the earth like a needle piercing through layers of sedimentary rock, shale, and sandstone. The average depth of a modern oil well is around 5,000 meters, but many major fields require drilling down to 7,000 meters to reach the reservoir. As the drill nears its target, high-pressure drilling mud is pumped continuously to stabilize the wellbore and prevent a dangerous kick, the precursor to a catastrophic blowout. At the surface, a high-pressure valve system, known as the Christmas tree, is installed to control the flow of oil and gas rising from the well. Every year, onshore oil and gas operations produce tens of billions of barrels of oil equivalent. In the United States alone, more than 900,000 wells are currently active, contributing roughly 1,112 million barrels of oil per day. With global consumption still immense, petroleum remains one of the largest economic pillars on Earth. The benefits of oil and gas are undeniable. They form the backbone of transportation, electricity generation, plastics, fertilizers, pharmaceuticals, synthetic clothing, and thousands of essential products that define modern life. A world without oil and gas simply could not operate the way we know it today. But this dependence comes at a cost. Many fields in the United States and Russia now rely on hydraulic fracturing or gas injection just to maintain production. The number of newly discovered large oil fields has dropped by 60% compared to the previous century, revealing a clear downward trend in global reserves. Slowly, the wells that once gushed like lifelines are falling silent. Humanity is realizing that it can drill deeper, faster, and more aggressively, but it cannot drill into emptiness. And as the horizon of accessible energy fades, the world is being forced to look toward places it once never dared to go. The Nestor Kirchner pipeline project does not conclude merely with meters of pipe buried deep underground. It opens a new chapter for Argentina's energy system. From raw steel plates in the factory to hundreds of kilometers of construction in the field, each stage plays a role in transforming gas trapped beneath the surface into a real flow of energy entering the economy. This stands as a clear demonstration of how infrastructure, engineering, and national strategy intersect. When a pipeline is completed, it does not only transport natural gas, but also carries a nation's energy autonomy and long-term vision. Mandarin Tech will continue to accompany you in exploring infrastructure and technology projects like these, where every technical detail is shaping the modern world.